algebra review. So let's just start. Arithmetic sequences. Arithmetic sequences have a common difference, so they either add or subtract the same amount to each term to get the next term. The common difference can be found by doing the second term minus the first one. That's all this means. All this means is second term minus first term. So when you see something like that, that's all that means. So if I give you a sequence that's like 6, 10, 14, yada yada, if you want to find the common difference, you just do one term minus the one before it. So my common difference would be 4. If you want to find the nth term of arithmetic sequence, it's given by this formula here. That's in your formula sheet. U1 equals the first term. D is a common difference. And then the term number. So if I was using this as my example, it'll be UN would equal U1, which is 6, plus n minus 1 times my common difference, which was 4. So that would be my formula, and then n would be able to term number. If you want the fifth term, plug in 5. You want the fifth term, plug in 6. If I give you a term value like 300, I want to know what term it is. Plug it into this part and solve for n. If you want the sum of the first n terms of arithmetic sequence, you can use the formulas here given by the formula sheet. So you just plug your stuff in. I prefer this one myself. A lot of people overthink this one. It is easier, but a lot of times you don't have u of n. So like you need like the fifth. If you want the 50th term, you need to have the 50th term here. So I actually use this one way more because I don't need that last term. And let's do a quick example. So the arithmetic sequence has u20 equals 62 and s20 equals 670. Find the values of u1, d1. So here's a trick. Anytime you're missing a term or two, you always go back to the original formula. So I'm going to go back to my original formula. Un equals u1 plus n minus 1 times d. So this is my un. So 62 equals u1, which I do not have, plus 20. It's the 20th term times d. So I have 62 equals u1 plus 19d. So that's that formula right there. Now, for this one, I gotta use that formula. I can use either one. In this case, I'm actually gonna use this one because I do have u20. So if I was using this formula, it would say s of 20 equals 20, because that's my n, over 2, u1, which I do not have, and then u20 I actually do have. So that's u20. And I have u20, 62. So I can simplify this a little bit. Oh, next to 20 I have is 670. So 10 u1 plus 62. Let's divide by 10. 67 equals u1 plus 62. So u1 equals 5. And since I have u1 equals 5, I could go back into here, sub it in, and find out what my d is. So 62 equals 5 plus 19d. Subtract 5. And I get 57 equals 19d. And I think d would equal 3. So there's my u1, there's my d, and then that's my problem. Geometric sequences, much like arithmetic sequences, except for now each one's multiplying are through multiplication or division. So you're either multiplying to each term or you're dividing to each term, which we consider 1 over a fraction. So for example, if I give you a sequence that was like 10 and 5, 5 over 2, 5 over 4, I would say r is 1/2. Right? You're divided by 2 each term, but we actually said you multiply by 1/2. So, and that's how you find your r. Easiest way to do it is u2 over u1, right? Just put one term over the one in front of it. So I could put 5 over 10, or 5 over 2, 5 over 2 over 5. You just plug a term over the one in front of it. The general formula is given by this, which you can find in your formula sheet. This you cannot. Keep in mind, r you cannot find in your formula sheet, but this general formula you can. If you want the sum of first n terms, just another formula you can find in your formula sheet right here. If you want the infinite sequence, so you gotta watch out for this one. So this is when you want to find the infinite sequence. So a lot of times I'll be asked you to do this, but without this saying it directly. If you're asking to find a sum and it happens to be infinite, you want to use this formula. It's a very simple formula. It's just u1 over 1 minus r, but that's only if r is less than 1, less than or equal to 1. That's the value of r. So all that means is it has to be getting smaller each time. So it can't be rising. So if I give you 2 sequences, one was the one I gave you over there, and then one was this. That one you could use it on because r is less than 1. This is 5 over 10, 1/2. Even if it switches signs, still good. R, the absolute value of r is less than 1. I could find that. I just do the formula, negative 10 over 1 minus my r, which is negative 1/2, and plug it in. I cannot use it on this one. My r here is 2, 6 over 3. That is too big, so you cannot find the infinite geometric sequence. It only works for numbers when the values are getting smaller. This is an example. A geometric sequence has a u1 of 2 and a common ratio of 3. What is the term number that will first exceed? Is it 1,000,000? So set it up. Our general formula is this: a1 times r to n minus 1. I want the first one to exceed 1,000,000. So I know my first term is 2. I know my common ratio is 3. I have n minus 1 is greater than 1,000,000. Well, this is just an algebra problem. I gotta solve for this thing up here. So remember, the way we solve with variables on top is we either find the common base, or you have to take the natural log of both sides, or log of both sides. In this case, we're gonna do that, but first we get rid of this 2. So I'm gonna get 3 to the n minus 1 is greater than 500,000. Now I gotta get rid of the base here because I cannot get these a match. So I'm gonna take the natural log of both sides. That lets me bring this n minus 1 down. So I'm gonna have n minus 1 natural log of 3 is greater than natural log of 500,000. Then all we gotta do is solve for n. So we're gonna divide by natural log of 3. I get n minus 1 is greater than natural log of 500,000 over natural log of 3, and then we're gonna add 1. The rest of this we have to use our calculator to figure out, because I don't know what the answer is. And something to that effect. And that's the idea. Summation notation. So summation notation, this sum right here, that just means sum. Sigma means sum. So all that really means is they want you to start here. You plug these values into there until you reach the top number. So for example, here it would be 4 squared minus 20. And then we're going to do 5 squared minus 20. And we'll do 6 squared minus 20. And then we'll do 7 squared minus 20. Right, so all we're going to do, we're going to start with this number down here, sub it into our equation until we get the top number. Then the sigma comes in. All this thing means is sum them up, add them up. So plus, plus, plus. When you add all that up, you get your answer. So that's summation notation. You can also do this on your calculator. If you go math, if your calculator is updated toward the bottom, there should be a summation notation. You can plug in and you see it. Now, this is, so you just type it in. That's the easiest way to do it. That's how you do this like that. But remember, there's 2 tests on the IB exam. There's one with a calculator and without a calculator. That's how you do it without a calculator. Look at the next one. When there are many terms, right at the first few, look for a pattern. For example, this. So again, if you use a calculator, just plug it in. If you don't have a calculator, write at the first few terms to find a pattern. So we're going to plug in 6. It's 3 times 2 to the 6, which is 3 times 64, which is like 192. And 3 times 2 to the 7th, which is 3 times 128, which is some big number I don't know. And you have to find a pattern with this. In this case, oof, these are ugly. This gives us 384, so that actually is just a times by 2, which I knew already from this thing right there. Anyway, this is a geometric sequence. Since we're looking for the sum, we need to see the summation notation of a geometric sequence. We use this formula right here. So that is s to the n equals u1 1 minus r to the n over 1 minus r. Our u1, we'll actually use our first term here. We'll make this our u1, so 192. 1 minus my r, that's my r. To the n power, so we're going from 20 to 16, 20 to 6. So I know it's 14, but you got to include the 5, so it's actually 15 over 1 minus 2. So between 6 and 20, we're actually doing 15 terms, not 14. I know you subtract 20 minus 16, but we actually use the 20 and the 16. So that's why it's like plus 1, it's actually 15. And that's the summation of that function right there. Logarithms, the expression log base 2 of 1 over 8. So this is a fancy way of saying it. I just always think of 2 to what power equals 1 over 8. So we can think of it that way. How do I go from 2 to 1 over 8? So 2 cubed is 8, but I got to flip it so it's negative 3. That's one way to do it. The other way to do it is we set this equal to x and then solve it, but we can talk about that later. You must be able to change an equation from log to exponential using the fact that blah blah. So you know how to rewrite this. And the trick to rewrite is just get the base. Take the base to both sides. So that's 3. You add that 3 to both sides. and then you get these cancel. You get 20 equals 3 to the x, which is actually not solving, but it's rewriting it. A better example to solve. Let's say if I give you log 2 to the x equals like 5. So it's the same trick. You take the base of both sides. These cancel out. You get x equals 2 to the 5th. So let's move on. If there's no base shown on logarithm, the base is going to be 10. So if we just see like log 3, that's the same as saying log base 10 of 3. And it goes the same if you're solving it. So let's say I give you log x equals 2. If I was supposed to solve this, you just rewrite it. The base is 10, they don't say it. So you take 10 of both sides. These cancel out. You get x equals 10 squared, or x equals 100. Similar for e. Natural logs have a base of e. So if you take natural log, it's the same as saying log base e of x. And that's why natural log and e's cancel each other out. So that's why if you get like natural log of x equals 4, if you wanted to solve that, you take the e to both sides. You get x equals e to the 4. Likewise, if you have e to the x equals 2 and you want to solve it, you take the natural log of both sides. And you get x equals natural log of 2. Logs are particularly useful for solving equations with variable is the exponent. So something to this effect. Let's actually get rid of that. It makes it so we'll get 5 to the 2x minus 3. Otherwise, I can solve it without a log. And then we're going to take the log of both sides. I actually like to take the natural log of both sides. It's a little shorter. Bring that to the front. So you get 2x minus 3 equals natural log of 5, natural log of 4. So since the variable's on top and you can't get the bases to match, if you get the bases to match, that's the best way of doing it. But since you can't get the bases to match, you take the natural log of both sides. That lets you move this to the front. It's in parentheses, don't forget. Then you take the divide by natural log of 5, and you get 2x minus 3 equals natural log of 4 over natural log of 5, and then solve for x. So add 3 divided by 2. Now when you add 3, do not combine it with anything. It sits on the side here, plus 3, and then when you divide by 2, same thing. You just get this ugliness of a mess that is all right. Something to that effect. Don't forget our log laws. IB loves using log laws. So if you're multiplying two logs, the same thing as adding them. So if you get something like this, you could write it like this. If you're subtracting them, you're dividing them. So likewise. And then the power one, I've used this one already, right? So if you have something as a power, so if I have x cubed, you can move that power to the front. So 3 log of x. Other facts, I've used this one quite a lot. If the bases match, they just cancel out. So that's all that's saying is if this is a 3 log 3x, these just cancel and you get x. So I've used that. That's how I solve logs, right? 2 to the x equals 7. You just take the base of both sides. That way these cancel and you get x equals 2 to the 7. E and natural log cancel out. We talked about this. This one's the same thing I just talked about. And then log, that's a good one to know. That if the base and the number are the same, it's just 1. And we can use that as a trick sometimes. Single log. So all this is saying is if you have a single, we did this earlier. So if you have a single log, the way you solve it, if it's like that, or actually it's like this also. The way you solve it is just convert it. Take the base of both sides to cancel it out. X equals 3 squared. Same thing here. Take the base of both sides to cancel it out. X equals 4. So if it's a single log, that's all you do. You just get the base of both sides to cancel it out. If it's multiple logs, you got to condense it first. Convert to a single log. Condense. So I can't just take the base of both sides here. I got to condense it first. So plus means multiplication. So I get log of x times x plus 1 equals log of 2. Now I can take the base of both sides. So the base here is 10. Essentially the logs cancel each other out. You get x times x plus 1 equals 2. If I solve this, I get x squared plus x equals 2. Set equal to 0. Factor. X plus 2 x minus 1. And then I get x equals negative 2 and 1. Now logs, in general, the domain of logs are x has to be greater than 0. So that would not be my answer. My answer is only 1. So that's how you do it. That's how you condense logs. You have multiple logs, you condense it first. So For another quick example, if I gave you log x minus log 3 equals 4, base 2, base 2. I gotta condense this first, so I get log 2 of x over 3 equals 4. And then, since I gotta rewrite it, or take the 2 to both sides. These cancel, I get x over 3 equals 2 to the 4th, and then you times it by 3 to get your answer. So x would equal 2 to the 4th times 3. So condense logs first and then simplify. Very, very important. This is all about using a trick. So recall that log, if as long as the base and number match, it's 1. So these cancel out. So if I use something like log 6 of 6, it's just 1. Log 7, 7, just 1, right? It's a common thing. We could use this to help us solve some logs. So if I was doing this one, I wouldn't know how to begin to start it. I got log 3 of x minus 2 equals log 3 of 4. So I like move this over, and then how to get rid of log? It gets messy. So I could try to do that. Remember, this is not 6. That's just log base 3 of 4 plus 2. And you take these to both sides. But what does that do here? That's just some ugly mess. That doesn't really help me. So what you could do is a trick here. We're going to write it like this. I'm going to make this 2 into 2 times log 3 of 3. Because log 3 of 3 is this 1, so it's still fair. Then what I could do is I move this 2 up, and I get this log 3x minus log 3 of 3 squared equals, that's an ugly 3 squared, equals log 3 of 4. Then I can combine, so log 3 of x over 9 equals log 3 of 4. The logs cancel out because they're both the same. X over 9 equals 4, x equals 36. So there we go. That's a trick you can use to help yourself out. Change of base rule. So basic change of base rule, you could split the base and the top number. So if I give you log of 3 of 4, you can make that log of 4 over log of 3. Or if you want, you can make a natural log of 4 over natural log of 3. And actually, it doesn't matter what the base is. You can make it log base 7 of 4 over log base 7 of 3. The general idea is this: you could split it. So if you have a log, you split top and bottom. Base goes to the basement, top goes on top. It doesn't matter what the base is. You can make any base you want. This is the thing Ivy likes to do. Log base a of 2 equals x, log base a of 5 equals y. Write the following in terms of x and y only. So they only want you to use x and y. So 2, so you have to think about how can I get 2 and 5. So let's see if I break this down. 20 is the same thing as saying 4 times 5. That's the same thing as saying 2 times 2. So I could break 20 to be 2 times 2 times 5. Right? Because I need it all in 2s and 5s. So then I can split this. Multiplication is addition. So log 2 plus log 2 plus log 5. And then here we go. Log 2 is, technically they should all have a base a. But now here we go. All the log base 2s are x's. And all the log base 5s are y's. So I get 2x plus y. Then you look at this one like, what's going on here? Log base 5 of 2? How do I do this? We're going to change the base rule. Top goes on top. Bottom goes on the bottom. Now here's the thing. Remember, I can make it any base I want. So I'm going to make these both a. There we go. Now this is x, that's y. Alright, so that's tricky, but that's a rule we can use. Use a change of base rule. Top goes on top, base goes in basement. You can make it any base you want. We'll make it base a to make it match. So then log base 2 is x, log base 5 is y. Binomial expansion. One of my favorite topics on IB and one of IB's favorite topics. They do this on the test every year. So binomial expansion is all about how we're going to expand this using the binomial expansion formulas. To know that, we need to know how to do NCR. If you could use it on your calculator, it's right on your calculator. So in your calculator, that would be, you put the first number in. Let's say we want to do like, let's say we do 5C3. On your calculator, you plug in the 5, type in 5. You go to math, you go to probability, and then NCR, and then 3. You should get 10. So That's one way to do it. Your formula book also gives you a formula, which is, if you want to do NCR, it's just n factorial over r factorial times n minus r factorial. It's not as bad as it looks. So this will be my n, this will be my r, so it'll be 5 factorial over 3 factorial, and then you subtract them. 5 minus 3 is 2 factorial. And the trick of simplifying this is you take the top number and expand it down. Remember, factorial just means multiply all the numbers beneath it. So 5 times 4 times 3 times 2 times 1. So I'm going to do that here. 5 times 4 times 3. I'm going to stop there because this is the same thing as 3 factorial. Why would I stop there? Because it matches the one on the bottom. And then 2 factorial, you just let it go. You simplify that. 2 times 1. Stuff cancels. 3 factorials cancel. 2 and 4 reduce, so 1 and 2. You just get 10. That's all it is. So like if I would give you, this for a quick example, if I give you 9c3, I'll be like 9 factorial over 3 factorial, subtract 6 factorial. I would expand the top, 9 times 8 times 7 times 6. You stop at the big one because that matches with that one. And then this one you expand, 3 times 2 times 1. These cancel. 3 and 9 reduce to 3. 2 and 8 reduce to 4. So this is 12 times 7, or 84. Or you could do Pascal's triangle, right? So you start with the 1, bring the sides down 1 and 1, bring the sides down 1 and 1. To get this 2 here, you just add the middle 2 terms. So you bring the sides down, and then you add these 2 terms, 3. Add these 2 terms, 3. Bring the sides down. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then bring the 1. So if I want an extra row, I'll bring the 1s down. Add these 2 up, and I get 5. Add these 2 up, I get 10. Add these 2 up, I get 10. Add these 2 up, I get 5. And so on and so on. How does this work? Well, let's say if I wanted 5c3 again. Trick here is you start with row 0. This is row 1, row 2, row 3, row 4, row 5. And you start with 0 again. So this is 5 0, 5 1, 5 2, 5 3, 5 4, 5 5. So 5c3 would have just been 10, like we got like that. Anyway, if I want to expand 2x minus 4, I use the formula. So formula always starts out the same way. Start with whatever the power is. So 4. Then you write the first term, and then you write the last term. And we move on. Oh, it says over 0. You go 4 over 1, first term, last term. And then 4 over 2. Erase this. First term, last term. 4 over 3. First term, last term. Finally, 4 over 4. First term, last term. Then we have to do the powers. The bottom power always matches the second one. And then these 2 powers should add up to be the top number, which is 4. So in this case, it'll be 3, 2, 1, and 0. Some people say they count up and count down. That is true, but a lot of times they ask you for a very specific term, so that doesn't help you. And then all we do here is simplify. Here's the key thing. If I want to do 4 0, I can do the formula sheet, or this is where Pascal triangle makes it actually really easy. 4 0 will be 1, so it'll be 4, 6, 4, and 1. Again, you can do that, or you can use some different ways of solving it. You simplify all these. 2 to the 4th is 16. Anything to the 0 power is 1. Now keep in mind, all things right here gets multiplied, so this is just 16. Then you go plus the whole next term. So everything within the term gets multiplied. So I'm doing this term here, it all gets multiplied. 2 to the 3rd is 8 times negative x. So this becomes negative 32x. Then we add the next term. So this is 4. Negative x squared is this x squared, positive. So I get plus 24x squared. Plus, I get 2. Anything to the 3rd power is a negative, keeps a negative. So negative 8x. And then this is 1, and this is positive x to the 4th. And that'll be it simplified. Let's move on to the next one. I'm actually going to do this one in 2 parts. So I want to hence find the coefficient x squared. So ignore the stuff we just did. Pretend I was asking just how do you find the x squared term in this guy? Well, if I want to find x term on this guy, so I'm going to do that part first. To find x squared in there, I would go, okay, start with 4. My first term is 2. My second term is negative x. I want x squared. So that lets me know that right here should be a 2. If that's a 2, this is a 2. and then this, since these have to be a 4, has to be a 2 also. So if I simplify this, I could do 4 factorial over 2 factorial, 2 factorial for my calculator. Anything I want to do, I'm going to get 6. This is 2 squared. This is negative x squared. So I would get 6 times 4 times x squared, which would give me 24x. So that's how you squared. So that's how you find the coefficient of any term you want. You just break down what you know. I know I have to start with the 4. I know my first term, my last term. Then put what you want. I want x squared, so that goes here. And that's a square that goes down there. And this has to be a squared also. I need to simplify it. So that's if I wanted to find x squared on number 1. Now if I want to do this whole problem, what they're actually asking me to do, it's a little more complex. So to do this, to find x squared in all of this, I'm going to go back to what we used before. We actually know what this is. It's up there. So I know all of that is 16 minus 32x plus 24x squared minus 8x cubed plus x to the 4th. And I want to multiply that by this guy, 3x minus 1. And all they want is x to the 4th term. Right, well, how do I, x to the squared term, sorry. How do I get x to the squared? Well, if I multiply 3x, the only thing that's going to give me x to the squared is when I multiply 3x by this guy. Because this means x to the first times x to the first, and that's going to give me negative 96x squared. When I do the second term, I'm going to multiply by all of these, but the only one I'm going to care about to give, that gives me the x squared term. And that'll be this guy times this guy, which will be negative 24x squared. Right, so when I multiply 3x by this term, they multiply to give me x squared, which is all I will care about. When I multiply negative 1 by the x squared term, that gets me x squared, which is all I care about. You add these two together, and you get negative 120 x squared. And that'll be the answer to that one. And actually, I'm a little off. It just wants the coefficient. Coefficient's just this number right there. So my answer is actually negative 120. If they wanted the term, that would be the whole thing. But coefficient's just the number in front. It's a constant in front of it. The number in front of it. The coefficient in front of it. The next one. Look at the patterns variable to find specific terms. Whatever. Find the constant term of the expansion. So here's the first thing. The constant term is x to the 0. So that's what we're looking for here. So we do what we always do. So I start with this. Here's to the 6. Write down what we know. I know this has to be 2x squared. I know this has to be negative 1 over x. And I want x to the 0 term. So this is where I do a little math. So let me rewrite this a little bit. So 6, 2x squared, negative x to the negative 1 power. So I'm going to do this. Let's make this a and b. And we're going to solve this. I want to get x to the 0. Well, what do I know? I know that a plus b has to equal 6. Because that's the way it works. You put these two together, it has to equal 6. And I know when I multiply these out here, so when I multiply this in, I get 2a, and I get negative b, and I want that to equal 0. So I'm looking for the constant term. So all I got to do to figure out what my term should be is solve this. So let's add these up. I get 3a equals 6, so a equals 2. So I know now a has to be 2, and if a is 2, b has to be 4. So let's go back to this one right here. Right? Now I know a has to be 2 because we just solved it. And if that's 2, if this is 2 and that's 6, this has to be 4. And if that's 4, this is 4. So all I gotta do is simplify this now. So I'm gonna get 6 over 4. 6 choose 4. Again, we can do in a calculator. I'm gonna use the formula I showed you earlier. 4 factorial, 2 factorial. So I'm gonna go 6 times 5 times 4 factorial. Stop there, because that's going to cancel out with this guy. Expand 2, 2 times 1. These cancel. 2 and 6 reduce to 3, and I just get 15. So it's 15, 2x squared, negative 1 over x to the 4th. Simplify this down. Now keep in mind, this square goes to both of them. A lot of people forget that. So it's 2 squared, x squared. So that'll be 15 times 4 times x to the 4th. This one, you're taking a negative to an even power. That makes it positive. So it'll be 1 over x to the 4th. Simplify. These cancel. I just get 15 times 4, which is 60. And that's the answer. That's it for this review video.